Hello, everybody. So this is our second to the last lesson on series, and more specifically, testing for series convergence. I am hoping this one's shorter than the last one. I think it will be. In fact, as we continue on here, learning these tests are pretty quick and easy now that we understand, hopefully, the underlying reasonings in what we're doing here. So we have a couple tests to look at in this video, and then a couple that'll be in the last video for a series. So you want to have your series flow chart ready. We're going to be looking at a couple series, as you can see here, the nth root test, the integrals test, the p-series test, which we kind of already have a hint about, and the limit comparison test. All of these individually are pretty easy. In fact, a lot of them are algebra-based or calculus-based in terms of actually doing calculus. So these you might feel a little bit more comfortable with. We will make sure that we make note cards to put these on, so flashcards, and we'll talk about which ones are really the kind of the main ones that are used on the AP exam and in terms of focusing. All right, as always, make sure that you pause me or back up and rewind. You want to make sure you've got an example of each one of these tests in your notebook so you can look from. And as always, too, please, please, please make sure that you're doing the practice problems that I'm going to be assigning. All right, let's go. All right, so in the last video, we started and we've been practicing with the ratio test. So if I've got a series with positive terms, and I take the limit of the ratio of the nth plus 1 term to the nth term, you know, we're usually given the nth term in my series itself. I take that ratio, which again, if you remember, we actually set it up as the a sub nth term, nth plus 1 term times the reciprocal of the a sub nth term. And we hopefully have done a bunch of examples of that. Okay, well, if that ratio came out to be a constant, we say that the series converges, and we say it converges absolutely because we took the absolute value of it, if the limit is less than 1. So, which is kind of, again, easy to think about because you're really trying to figure out what the ratio is. What is, as if this was kind of like a geometric series where you're multiplying by something to get to the next term. What is that ratio to get to the next term? Well, I need the terms to at least get smaller, and they'll get smaller if that ratio is something less than 1. So that's an easy way to remember it. Obviously, if the limit turns out to be something bigger than 1, you're multiplying. You would think about a geometric series. You'd be multiplying something bigger than 1, it would grow, not converge. And if it comes out to be equal to 1, well, then this test is inconclusive. We're going to have to then go and choose another one of our tests on our series flow chart. All right, so that we've done already. So let's examine some other tests that we can use to discuss for convergence or divergence. Now, in the end, just remember that we may not actually know what this series converges to. There's very few series that we actually know what they converge to. Geometric series, we know they converge to a over 1 minus r. And we also looked at telescoping series. We know what they converge to, as all of those terms cancel each other out, those positive negative terms. You can easily see what the first couple terms would sum to. So let's take a look at the nth root test. All right, so the nth root test is this. So if I have a series with an a sub nth term with positive terms, now this one is set up with positive terms. If you actually look at your series flowchart, you'll see they don't have that stipulation that the terms have to be positive because they put an absolute value around that. Well, if the limit of the nth root of a sub nth term comes out to be a constant, then the series converges if the constant is less than 1. The series diverges if the constant is greater than 1. And the series is inconclusive if that constant is equal to 1. So that limit, whatever that limit comes out to, will tell me whether or not that series converges or diverges. And note, this is exactly the same rules as our ratio test. So the nth root test and the ratio test, we like to kind of think about together. That's why they're both together at the bottom of your series flow chart. So let's look at this in action and kind of also see the biggest problem, I don't want to say problem, but the biggest challenge we'll have is deciding which test to use. So when I have a series that looks like this, now again, we're talking about series of numbers, and we're not talking about power series. So a series of numbers. Now, first of all, you can go and write the first couple terms of this. Put a 1 in for n, put a 2 in for n, put a 3 in for n, and then you start writing those terms out. with addition signs in between, and we could kind of look to see what's happening as we look at some partial sums. But the giveaway that I want to use the nth root test is that I have a term with the nth power. Because terms with an nth power, I can easily take their nth root. So here I'm going to go and take the nth root of this expression. And let's simplify it a little bit. So there we go. That's the thing that I really like to see. The nth root of 2 to the n is just 2. Now up in the numerator, the nth root of n squared. So again, remember, we're going to be taking the limit of this nth root. So let's go off to the side and figure out what the limit is of this. This will be a good little practice. This might be an overstretch of the kind of example you'll see on the exam, but so the question is, what is this limit? So again, I can take the nth root and then of the n squared, or I can take the nth root of n and then square it. It doesn't matter the order that I do that because I'm taking powers to powers. So the question is, what is this? So I'm going to go off to the side and figure this out. All right, so let's just figure out the limit of the nth root of n. So that can be written as n to the 1 over n. If I put infinity in here, I have infinity to the 1 over infinity, so infinity to the 0. Ah, this sounds familiar. So we've got to change it to our exponential change that we did with L'Hopital's rule earlier. Probably already know what's going to happen next here. That 1 over n comes down out in front. All right, and I want to get it into L'Hopital's form, so I just rewrite that as a fraction. So I have the ln of infinity, which is infinity over infinity, infinity over infinity. So sure enough, yeah, here comes L'Hopital. And I think all we need to do is one derivative to get rid of that n, so it becomes 1. And then at this point, 1 over infinity, well, that'll go to 0, and e to the 0 is just going to be 1. So there we go. That's that term. So let's put it back in context. So here's that term. Now it's going to be 1 squared. So now we go back to my original limit. And so therefore, the limit of the nth root of this a sub nth term is then going to just be 1. That's what we just figured out, over 2. Well, 1 over 2 is a fraction that is less than 1. So therefore, this series converges. Oops, let me go back and just say something here. It converges, but I don't know what it converges to. 1/2 is not what this series converges to. All we did was a nth root test that came out to be a constant. We just know that this series converges, and that might be all we want to know. All right, so what if I look at this example? So maybe can I give you a second to maybe set this up as a limit and see where to take this from here? Go ahead and pause me and see what you do with this one. This one should not be very different, you'll see. All right, so if I set this up and taking the nth root, I really should write the limit out in front here. I'm just going to simplify in this case. So this is what I'm really going to wind up taking the limit of. And I think we already did the legwork for this thing down in the denominator here. That was the same thing we just did. So that's 2, or 2 over 1. So therefore, that comes out to be 2. That is a value that is greater than 1. So therefore, this series diverges. But wait a second. I will tell you, if this was me and I was given this series and wanted to know whether or not it converged or diverged, I would first look just to see what happens as the terms get bigger. I would actually use the nth root test. Sorry, not the nth term test, I should say, not the nth root test. The nth term test, which is my first test in the top of my series flowchart. What happens as n gets bigger and bigger and bigger? Well, 2 to the n over n squared, well, the numerator is going to grow much more quickly. That exponential function is going to grow much faster than n squared. Hey, all it would take is 2 L'Hopitals to see that this limit of this expression would turn out to be infinity. So therefore, the numerator is growing faster. This limit's going to head to infinity, which means the terms get bigger and bigger and bigger. If the terms keep getting bigger and bigger and bigger, then there is no way for this series to converge. The terms have to get smaller to be even possibly convergent. So this I would have proven by the nth term test. I would have said that since this limit of this ratio goes to infinity, this will diverge. So again, there will be multiple ways for us to solve whether or not these series converge or diverge. So I welcome you to ask in class and look at examples to see, hey, maybe I solved it one way. Could I have solved it a different way? All right, so that's nth root test. So now remember when we studied integrals, we used a summation of rectangles to approximate the area under the curve. So here's my Riemann sums. Well, this leads to an integral test. So the integral test, which is a pretty common test as well. So if I have a series with an a sub nth term, and it's a positive series, or sequence of numbers, I should say, but we would be adding these up for a series. As long as we call that a sub nth term, let's going to call that a function. And if that function's continuous, positive, and decreasing on the interval from n to infinity, then if the integral from n to infinity converges, then this series will converge. If the integral diverges, then this series will diverge. So you can see right now with this limit to infinity, we are definitely going to be talking about doing improper integrals here, so which is why we learned them before this. So the three big conditions, these are the conditions you have to know for the exam, is that for the integral test, it's got to be continuous, which this graph is, positive, which this graph is above the x-axis, and decreasing. Well, this graph wouldn't work, so I would have to see a graph that comes down like this. So that is my integral test. And if you look onto your series flow chart, you will see those conditions are right in that box: continuous, positive, decreasing on a to infinity. All right, so let's look at an example. So the question is, does this converge? All right, so does this series converge? So we're going to check and integrate this because it seems like a function that might be easily integrable. So I'm changing my n's to x's. And I'm going to integrate it from 1, whatever this value of n is, that's my lower limit, up to infinity. And I want to simplify this a little bit with two things here. I'm going to swap out my limit so I can deal with this improper integral and also rewrite this as a power. So this is x to the half times x. So 1 over x to the 3 halves or x to the negative 3 halves. Sure enough, antiderivative, simple, simple. We've been doing these for a while. Put in my upper limit and my lower limit. Keep bringing that limit along. I haven't evaluated it. So now as b approaches infinity, we can clearly see that this comes out to be 2. So what does that mean? Well, that means that this improper integral converges to 2. The area underneath of this function accumulates or approximates to an area of 2 or approaches a value of 2. Well, then that means my original series converges as well, but it doesn't converge necessarily to 2. I don't know what this series converges to. So again, it's not a geometric series. It doesn't seem to be a telescoping series. So at this point, I might just be happy to know that it converges. Now I'll tell you in the future, near future here, this particular series, I'm not going to do this way in the future. I'm going to look at this, if I see this as 1 over x to the 3 halves, that sounds familiar. Sounds like a P series, which we'll talk about soon. There's definitely an easier way to do this, but it was an easy one to integrate. All right, so how about applying the integral test to this series? I want to see if this series is convergent. Now, how do I know I probably want to use the integral test? Well, I probably want to use the integral test because this seems like a function with an easy antiderivative. I'm almost looking at this as a 1 over u with a du kind of a thing. So let's just check our 3 conditions. All right. So is this function positive from n equals 1 to infinity? Yeah, that's only going to create positive terms. N squared will be positive. N's only going to be positive, so that's good. So is this continuous? Do I have any jumps, holes, or asymptotes? Well, let's check. If I set the denominator equal to 0 to look for any kind of discontinuities, I'd be taking the square root of -1 if I set this equal to 0. So that's imaginary. So we're good to go there. So definitely continuous. And is it decreasing? Well, what's the limit as n approaches infinity? Well, the numerator and the denominator is going to grow faster. So that denominator is going to get bigger. So I'm going to have like 1 over infinity, which will approach 0. So yes, that is decreasing. So we're good to go there. So the question is, let's find out whether or not the integral of this nth term of this series it converges or diverges. Go ahead and pause me right now. This is an easy improper integral. Go ahead and do that and see what you come up with. All right, so what's our conclusion? Well, here's my work here. So it became a 1/2 ln of x squared plus 1 from 1 to b. And when I substitute that in, I get infinity minus a 1/2 ln of 2, which is infinity. So therefore, this improper integral diverges. The area underneath of this graph keeps growing and growing and growing. But that conclusion means that my series, if I were to write out all the terms in this series, the sum of those terms would just keep getting bigger and bigger and bigger. It diverges. All right, you want to do one more? This is a good one too, which practices something else here. So go ahead and pause me, turn this nth term of this series into an improper integral and see if that improper integral converges or diverges to make our conclusion. All right, the conclusion should be that it converges. So now you should have gotten that it converges to pi over 4. The improper integral converges to pi over 4, but that does not mean the series converges to pi over 4. So show you my work here because there is something that you should be aware of. So my improper integral turned into a limit, inverse tangent, easy, straightforward. The inverse tangent of infinity, here's my inverse tangent function, it approaches pi over 2. You should be aware of that. And then the inverse tangent of 1, what tangent of what angle gives me a value of 1? Well, hopefully you know that's 45 degrees, pi over 4. So that's how I got pi over 4. So therefore, this original series does converge, but it doesn't converge necessarily to pi over 4. So again, we use the integral test when I'm given a series, nth term, that looks like a function that would be easy to integrate. Check the conditions, check for convergence and divergence, and then you're good to go. All right, so the problems with the integral test is that sometimes you might not be able to tell if it's positive, continuous, or decreasing on that interval. And sometimes you might not be able to find the antiderivative. If you cannot easily find an antiderivative of the nth term of a series, do not use the integral test. In fact, you can't. You're going to have to use some other test. All right, so let's get to one of our second best friend. I would say they're almost tied between that and a geometric series. Geometric series kind of eke out a little bit because we know what they converge to, a over 1 minus r, as long as r is between -1 and 1. But for a p series, these are easy to spot, and this should look familiar. If I have a series that's 1 over n to the p power, so it'd look like these terms here, well, that series converges if p is greater than 1, and diverges if p is less than or equal to 1. So remember back to improper integrals? So we were looking at those p functions. So yes, that's these. So, and it follows those same rules as what we had done before. Now, we can show this actually through the integral test, and you could, if you're interested in doing that. But just be aware that this seems a little backwards to the ratio in the nth root test. So in this time, it converges if p is greater than 1 and diverges if p is less than 1 because of the reciprocal nature of this expression, because those p terms are really down in that denominator. So we're going to kind of get that opposite relationship. So if you look at your series flowchart, you can see it is the second thing listed. It actually ekes out above geometric series because when we're doing series convergence, it's an easy one to spot. So we like that one. So if n is greater than 1, or sorry, if p is greater than 1, then we have convergence. So this is going to be our go-to a lot. So the question is, does this series converge or diverge? So now, granted, if I turn this into a function, I could do an integral test on this. I think this function is positive. It is continuous from 1 to infinity. It's not continuous at 0, but I'm not dealing with that. And it does decrease. This will get smaller and smaller and smaller. So I could do this through an integral test, but look, it's 1 over n to the second power. That's a p series. So therefore it converges because p is greater than 1. Boom, done. So we like these. Now I will say you're not going to be given a lot of these straightforward, but we're going to use this when comparing to other functions. We could use these when we go back to our direct comparison test. We might want to compare to p series, and we'll see a limit comparison test here in a minute. Particular p series here, when n to the first power, so this is p equals 1, gives me, this was literally the first series that I showed you. 1 plus a half plus a third plus a fourth, this diverges. Diverges, now we know because it's a p series and that p-value is 1, which is less than or equal to 1. Now, however, if this was alternating, we're going to wind up seeing that the alternating harmonic does converge. We saw that maybe in the last video as well. So yeah, this is my harmonic series. So we're going to use, again, as I said, we're going to use it to compare with a lot of other series. Okay, and again, you could prove this also because it's very easy to anti-differentiate 1 over n. So you could use the integral test to prove that this also diverges. So let's talk about this limit comparison test here. So we were doing direct comparison test where we could tell, you know, if I have a convergent, if I know I have a converging series and then I have a series that's bounded below, well, that series will also have to converge. And then the opposite is true. If you have a diverging series and a series that's above it, well, you know that series will diverge. Well, here is a slightly different approach. So if I have two positive series, the series are both great, all the terms are greater than 0. And if I take a limit of the ratio of those terms, so a limit of the ratio of those two terms, again, this is not like the ratio test where I'm dealing with one series and taking the a sub nth term over the a sub n plus 1 term over the a sub nth term. These are two separate series. So I'm probably given the a sub nth series, and then I'm going to pick another series to compare it to. And I'll talk about that in a second of how to pick them. Well, if the ratio of those series comes out to be some constant between 0 and infinity, then they either both converge or both diverge. So if you pick a series that's diverging and set this ratio up and get a constant, well, then your original series diverges. So it's almost like when you pick a series that's either converging or diverging, you already know you're kind of on a path of proving convergence or divergence. Well, what else is true? Well, if that ratio comes out to be 0, then my original series converges if the series I'm comparing it to converges. And also, if it comes out to be infinity, then the original series that I have diverges if b sub n diverges. All right, so this is my limit comparison test, and this is also on my flow chart. And you can see it's right next to the comparison test, or on the flow chart, the comparison test is the direct comparison test. All right, you can see those inequalities. All right, so we want to use this test to compare a series with an unknown behavior to a series with known behavior. And as I said, we're usually going to compare it to p series because we easily know whether or not they converge or diverge. So when selecting a p series, you want to use the same degree numerator and denominator as the given series, but disregard all the highest powers of n. So I'll show you what that means. We want to think about, again, we're heading out to infinity, so we only want to focus on the terms that are going to have the greatest influence out towards infinity. So let's take this particular series. More than likely, we'll probably be just given this summation of the a sub nth term. And here's some terms, but just kind of seeing, okay, so I'm adding up these numbers and I want to see whether or not this converges or diverges. Okay, so this does not look like it's easy to integrate. So that's going to be hard. It's definitely not a p series. So in and of itself, it's not a p series. It's definitely not a geometric series. It's not of the form a over 1 minus r. I'm sorry, it's not of the form of something to the nth power, I should say. So let's see what we can maybe compare it to. Okay, so as I said, when n gets really, really large, that plus 1, that's not going to amount to much. Same with this plus 1. Heading out to infinity, that's not going to amount to much. So we really ignore those. So therefore, I get this expression which simplifies to 2 over n. Well, 2 over n is greater than 1 over n. And 1 over n is a p series. That's 1 over n to the first. Now it's a diverging p series, so I think I'm on the path to proving divergence here if I'm going to be comparing it to 1 over n. Let's see. So I take my given series, all of the terms themselves, and I take this p series that I want to compare it to. Okay, so all of this work that we did here before was just to pick a p series that I know I can work with. Again, this diverges. So if this comes out to be, this limit comes out to be a constant between 0 and infinity, I know that my original series will diverge. So then this just becomes a little limit exercise, doing a little distribution through. And obviously you can see now why we've spent time on L'Hopital's rule earlier. L'Hopital comes to the rescue here. And I don't even need to show, but that's going to you would even know through the end behavior model this is going to approach 2. Hey, 2 is between 0 and infinity. That means it is going to also diverge. So since my series I compared it to diverged, that harmonic series, the given series will diverge as well. So how do you know when to use the limit comparison test? Well, when you can kind of look at an expression and first of all, integral test fails, geometric series fails, it's not a p-series. So I would then maybe try to see if I can simplify this to find a p-series that I can compare it to. All right, how about this one? All right, so just writing a couple terms so you can see what's happening. The terms are indeed getting smaller, so that's a good sign. So this is on the path of possible convergence. So again, the first thing we should always be looking at is to see, okay, does this ratio approach 0 as n approaches infinity? Because if it doesn't, if it gets bigger, boom, done, it diverges. So the first thing we should look for is the nth term and see if it diverges. All right, so I want to compare to something. So when n is really, really large, this little -1 isn't going to amount to very much. So it's going to behave a lot like this 1 over 2 to the nth. So let's compare it to that. So I'm going to set up my ratio. So here's my given series in the numerator over this series that I'm going to compare it to. Now, I haven't said whether or not I know whether or not this converges or diverges. Let's pause and talk about it. Is this a p-series? It is not, because the p-series would be 1 over n to a power. So what is this? How can I compare? I have to know whether or not this converges or diverges, or else I would not know whether or not my given series converges or diverges. Well, remember, 1 over 2 to the n, let me grab my little pen here real quick. That can be written as 1 over 2, the quantity to the n. This is a geometric series. This is a geometric series. I keep multiplying by a half over and over and over again. And what's true, that half is between -1 and 1. It's within the interval of convergence. So therefore, this is a converging geometric series. So again, p-series and now geometric series are going to be my two most common series that I'm going to want to do my comparisons to, either with a direct comparison test or a limit comparison test. So let's finish this limit out. Do a little reciprocal work, and hopefully you can see the limit as n approaches infinity is just going to come out to be 1. So therefore, if this comes out to be 1, 1 is between 0 and infinity, comes out to be a constant. I knew that the series I compared it to converges because it was a geometric series, so therefore my original series will converge. The only thing is I have no idea what it converges to. I don't know what this would ultimately equal. That's very rare that I know that. Again, it's only in geometric and so far telescoping series that I actually know what it converges to. All right, that's it for today. You can see there's just a couple more things on our sheet to be taking a look at, and not very much actually, so we're in good shape here. So hopefully this was a little bit easier to digest than the last video. Please, please, please make sure you're practicing these problems over the next couple days. Don't let me saying help. Ask for help, but I don't think these should be as bad as some of them that we did before. All right, guys, good luck.